Is that on?
I don't know.
I think it's fine.
Is
Can
it
you
on?
tap it?
Can you hear me?
Yeah, I think it's on.
It's on? Okay, good. Sorry about that. Okay. Good morning, everyone. So I'm going to try and talk today about how we can use lots of different exoplanet and companion detection methods to get to this multi-measurement approach where we really fully comprehensively understand the companions that we're looking at. So I'm going to try and talk about lots of the different results that have come out in recent years, and obviously this is a non-exhaustive list, and there's lots of great posters and talks happening today that are going to talk a little bit more about this approach. So I showed this exact slide in Leiden a few years ago, and I think it just encompasses exactly what I'm trying to portray. So I just wanted to start here. So imagine that we have all of these different detection morphologies, so like astrometry, radial velocities, imaging, even transits, and they all make up different ingredients to a cake. And I'm worried that this community here, myself included, has kind of been doing this. Imaging, nailed it. Instead, we want to get to this, where we're bringing together all of these different morphologies to go from looking like some disastrous cake to some beautiful, delicious thing. So we're going from more than just having like this imaged point spread function and saying we know what it is we're looking at, but actually fully comprehensively understanding the things that we're looking at. So there are kind of two pillars to this approach and to this talk today. So I'm going to talk both about increasing the detection efficiency by using this precursor information. So if we can use the information that we have in hand before we go forward to high contrast imaging observations, then that's actually going to increase our efficiency in our high contrast imaging observations. And then the other aspect of this, which I really want to hone in on, is comprehensively characterizing the companions that we do detect using this approach of this like multi-measurements approach. So because not everyone in the room is maybe focused on this component, I just wanted to get everyone up to speed and make sure that we understand the things that we're talking about here. So the first of those being the radial velocity technique, and I want to emphasize the parameters that you learn from each of these different techniques and how they can complement one another. So radial velocities is an indirect detection method. We focus on looking at the star rather than the planet. I know we're not usually interested in doing that here, but there is a lot to be learned. And as the companion orbits around the center of mass and we see this Doppler shift in the star, then we can get the parameters like the minimum mass of the companion that is orbiting around that star. And I'll emphasize the minimum mass because it's an unknown orbital inclination, so it is not the true mass. We also get a handle on the orbital period if we assess this over time. And so those are two very important parameters in order to understand the systems. The other aspect, which is another indirect way of looking at planets or brown dwarf companions, is astrometry. So rather than looking at these things in sort of the radial direction, we can measure the path of stars, of their proper motion over time. And if there's perturbations from that expected path, then that could be caused by a tug of a companion that is causing this perturbation. And we can measure that astrometry and combine that with the radial velocity information, as I just mentioned before. So this is kind of the astrometry approach. And I'll give credit to Kyle Franson and Brendan Bowler, who show a similar graphic to this, and I think it's a beautiful way to depict this. But there's sort of two main missions when we talk about astrometry here. So the European Space Agency Hipparcos mission from the late 80s, early 90s, through to Gaia much more recently, only recently just decommissioned, but still with much more exciting data to come. And over this 25 to 30-year baseline, we can measure this astrometric acceleration. And if we see a shift in that acceleration, much like the previous slide I showed you, then that can give us hints towards the astrometric acceleration of an unseen companion, which may be observable using high contrast imaging techniques. So that's what I'm talking about here. And credit to Tim Brandt for this, who's done a lot of work in putting together the Hipparcos Gaia Catalog of Accelerations, or the STScI. So Tim has put together this incredible catalog where you can go and look for your favorite system, your favorite star, to see if there could potentially be signs of a companion in that system. And these are the sort of measurements that we're getting here. So that Hipparcos measurement, that I mentioned from here in the early 90s. And then another point up here from Gaia, and this is Gaia DR2, but we've also done this for Gaia DR3, but also measuring the difference between these points as well gives you that sort of third data point to fold into the astrometric information. Okay, so how do we use this information? So we have the radial velocities in hand, we have the astrometry in hand, and what we can do is do an orbit fit of that information together, and that removes the degeneracy of the unknown orbital inclination. So remember I mentioned that the radial velocities only give you the minimum mass. This gives rise to the inclination if you have the astrometry. And here I'm just showing an example of what a prediction plot might look like for a prediction of a companion position relative to its stellar host. And this is really powerful precursor information that we can use to say, is this thing observable? Is it widely separated enough, given the information I know about the inner working angle of the chronograph I'm working with, for example? Is it in a favorable position in its orbit? Because some of these things get pretty close to the star, but it might be eccentric that if you give it a few years, it will be much more favorable to observe it. And it gives you information about the mass, so you can take some predictions about the expected contrast. And that's where the increasing the detection efficiency comes in, because you can really plan your observations with this information in mind before you even get to the high contrast imaging stage. So I keep mentioning mass, and I think that's a really important parameter. And the way that you might do some of the orbit fitting here, and I'll emphasize that this is a non-exhaustive list, but I've been showing some orbit fits from Evara, which is spearheaded by Tim Brandt, but here's a couple of other open source orbit fitting software that you might want to play around with and try. Octofitter is written in Julia, but don't let that scare you. It's very efficient orbit fitting code. Orbitize by Sarah Blunt is also really great and uses the OFTI algorithm, which is orbit fitting for the impatient. So if you're thinking, I don't have a radial velocity curve with like all of the orbital period in line, you don't necessarily need that. But obviously, proceed with caution if that's the case, but this is just some examples, some orbit fitting software if you're interested in playing around with this approach. Okay, so this is the mass cautionary tale, and mass is a fundamental astrophysical parameter, property of the things that we look at. If we don't understand the mass of the things that we look at, then we can't truly investigate what it is we're looking at. So I'm showing here an example of HD 92987, and I'm just showing this as an example because it's a bit of an extreme one, but you see here an orbit fit on the left and these beautiful radial velocities on the right. And this is an example of me sort of killing my own planet. So published this radial velocities back in 2019, which was the only data available for the system at the time. And it was about 17 Jupiter masses, so potentially a giant planet or at least a low mass brown dwarf. Venner et al. In 2021 folded in the astrometric information when that became available and actually was like, hey, this thing is a low mass star, this is not a planet. And then yes, lo and behold, imaged it with SPHERE and confirmed what Venner et al. Had established and folded in that additional astrometric information from imaging and was like, yes, this thing is a low mass star. And that's okay, I'm okay with killing one of my exoplanets. But this is so important because you cannot establish the testing parameters if you don't fully know the true mass of the thing that you're looking at. So just be cautious of that, and this is why dynamical masses are really important. Okay, so to bring all of this together, the radial velocities give you the minimum mass. They give rise to some constraints on the orbital period. The astrometry, when you fit that together with the radial velocities, can give rise to the dynamical mass and remove that degeneracy of the unknown orbital inclination. And then what I'm going to move towards speaking about as well is how that direct imaging folds in. So as I mentioned before, not only do you increase the detection efficiency, but you get additional astrometry if you get that detection that you can fold into your orbit fitting as well. So relative astrometry in addition to the astrometric accelerations I'm talking about. And as Marshall Perrin said yesterday, if you can image this, then you can get spectra of it. So if you can image your companion, at least with JWST, then it's likely that you'll be able to get some nice spectroscopic information of the companion itself. And again, that is really powerful because then you can fully understand the object that you're looking at. So all of this leads to comprehensive characterization. So the different components I'm going to mention today are ground-based radial velocity surveys. So I already showed you some radial velocities from before, which came from the Coralie survey, but there are many ground-based radial velocity surveys that are happening in parallel. I won't focus too much on this today, but I know there's a few people in the audience who are leading different efforts on the radial velocity front. Hipparchus and Gaia are really the workhorses of the astrometry here, especially Gaia, and we're anticipating Gaia DR4 by the end of this year, so I think that's going to give us even more important information, so that's going to be super exciting. And then the high contrast imaging and spectroscopy component, and this is across many ground and space-based instruments. I'm showing JWST here, but it's not just JWST. There's lots of ground-based and telescopes that are doing this as well. And I think Roman's also going to come into this in the near future and be very powerful. Okay, so I've mentioned spectroscopy, and I'm talking about spectroscopy of the companions themselves. And the reason why I really care about this is there's really only two techniques that give rise to the spectroscopy of these exoplanets and brown dwarf companions that I'm talking about here. And that is both the transit technique or direct imaging or direct spectroscopy. So if you haven't ticked this one off on your bingo card yet of your mass separation parameter space, here's the plot for you. And I know, here we're very familiar with this idea of filling in this parameter space, especially in that top right corner with these massive companions at wide separations. But what is happening over time, as some of the talks alluded to yesterday, is as we go to larger telescopes, more sensitive instrumentation, more sophisticated coronagraphs, more sophisticated post-processing techniques, we're going down in the sensitivity that we're able to establish in terms of lower masses, more extreme contrast ratios, and I think that's only going to continue. And also working inwards a little bit as well where possible in terms of the inner working angle, and so that's a proxy for the semi-major axes we're able to go to, as well as the masses. And transits, I think, are trying to push out a little bit in the other direction as well, or at least some people, and I'm really hoping that we can kind of meet this middle ground some point in the future. But the really important thing I want you to take away from this plot is the ones highlighted in bold there are the ones that have spectroscopic information of the companions. And so it's not just about filling in this parameter space, which is important, but it's also about understanding the different objects on this plot to really sort of understand the nature of these things, because they're not all the same, okay? So I think it's both. And so we really need to be able to do direct spectroscopy of these things to fully get there. And then, yeah, I've sort of crudely outlined where Gaia DR4 is going to start to come in terms of the sensitivity here. I'm not going to talk too much about Gaia DR4 today, but I do want to acknowledge it, I do want to mention it, and I'll call it now that at the next Spirit of Leo conference, there will be an amazing review talk on the results that come from Gaia DR4. I'm sure of it, so yeah. So what can we do from the ground in terms of high contrast in supporting this multi-measurement approach I'm talking about? So I'm just showing an example here of some spectra, sort of lower resolution spectra that we have with sphere, VLT, and then through to gravity in the sort of K-band there at sort of moderate resolution. So there's many ground-based observatories that are doing, they're covering this sort of wavelength range in terms of what we're able to do with spectroscopy and chronographic imaging. This is a J-band image I'm showing on the left here from sphere. But beyond about 3 microns or so, it does become very difficult from the ground. The thermal emission becomes quite excessive. And so we really want to be able to complement, I'm not even just talking about complementing multi-measurement techniques here, but complementing what we can do from both the ground and what we can do from space. So this spectrum was showed yesterday many times, but I think this really sort of set the benchmark for what we are able to do in terms of spectroscopy with space-based instrumentation like JWST. So VHS 1256, the first direct spectrum of the substellar companion with JWST, and we're starting to see this whole beautiful array of different elements, different molecules in the spectrum here, and including the first hints of silicate clouds there. So this kind of set the precedence in a way of okay, what can we do in terms of spectroscopy with these objects? What if we could combine benchmark objects for which we have the masses, for which we have the orbits, and then incorporate spectroscopy as well? Working sort of hand in hand with a lot of folks from the JWST Telescope Scientist team, a lot of this work spearheaded by Marshall Perrin, who gave a great review talk yesterday, kind of talking about how can we go from this sort of almost proof of concept that the amazing work that the early release science program team had done, and really start pushing down to getting these images and spectra of companions without a coronagraph using JWST, for example. So I'm just showing an example setup of a companion here. with a specified V3 position angle on the NeurSpec IFU. So there's no chronograph here. And this is how we're setting up these observations to avoid being occulted by a bright diffraction spike from the star itself or ending up in an IFU slice that would cause saturation where the companion is, because we want the spectrum of the companion itself. And so I know JB is going to talk later a bit more about like the data processing components of this. But one companion that we looked at is this benchmark brown dwarf system, HD19467, that was also mentioned yesterday, was published by Keelan Hoke in 2024. And so we have this beautiful orbit fit that we see here on the left. This is with Avara, and radial velocity is on the right. And you get these really tight constraints of where the astrometry, like where the object resides in this orbit fit. And that allows us to set up the observations, like I mentioned before in the previous slide, to ensure that you can get the spectra of such a companion. And so that's what we were able to do. And as I mentioned, see JB's talk later, who is going to dive into sort of the more technical aspects of how we're doing this, but we're forward modeling the 2D detector images to disentangle the star and companion signal. And so what you're seeing on the right is the detection of the benchmark brown dwarf that I just showed you, for which we have this beautiful orbit fit. And so this is the power of that. We have now the mass, so we can use this as a laboratory to like test the atmospheric models. So we're not only just saying, okay, we have this thing and we know it's this certain mass, we're actually able to establish this as a testing ground, essentially. So then this is what it looks like if you start combining everything together. So we have some ground-based, low-resolution data with SPHERE on the VLT, and we start to probe out to that sort of 2.5, 3 micron onwards range that NeurSpec is really powerful looking at. And if you zoom in here, we can really start to see what's going on with these observations. And I'll emphasize that prior to the NeurSpec observations, the only data in this wavelength range was this one black point here in the L prime band, which to go from that to having this wealth of information that we're able to look at spectroscopically is so powerful and so incredible, and especially where amount of the luminosity resides in that area. And so this is a really well-established benchmark brown dwarf system. These benchmark brown dwarfs, we have the masses, we're able to look at them in this way and really start testing what we know. And so from Keelan's work, looking at the spectra in this range, she was able to establish that we have a disequilibrium chemistry at play here and a bit of an interplay between CO2 and CH4, between methane, and that methane prefers a lower vertical mixing values in like some range of the spectra versus CO2 preferring a higher vertical mixing value in other ranges. And so this is what I mean when I'm talking about comprehensively characterizing these things. We're going from what we used to say, hey, here's an image of a point spread function. That's great, but this is going way beyond that and saying we know the mass, we know the orbit, we know what the spectra looks like. And the amount of, if we're able to increase the amount of objects for which we're able to do that, then that's great. I also want to mention, also from the JWST telescope scientist team, Kim Wardwong, who has a poster here, has been doing incredible work on GJ758. So Alex gave a talk yesterday where he mentioned some of the observations in the NeurSpec range on this. But we also have MIRI chronography observations, so out at those longer wavelengths. And you see the chronographic images here in the 10.5 and 11.5 microns, and the beautiful orbit fit of GJ758, which is another one of our beautiful benchmark brown dwarf systems. And again, incorporating this MIRI data with the NeurSpec data and with prior near-infrared data is just a really powerful tool to use these as test subjects. And I highly encourage you to go and check out Kim's poster so she can tell you all about this. Okay, some of you were present at this workshop a few years ago now. I wanted to acknowledge this. So Laurent and I put together this workshop, and it was a little bit sort of ad hoc, and we didn't quite know what we were doing, but we got there in the end. 2023, and we kind of put together a bunch of people in a room, and we're like, let's just talk about dynamical masses, and let's just come up with a bunch of proposal ideas, and we want to hear what people have to say. And we came up with about 25 or so JWST proposal ideas. This was just ahead of the cycle 2 proposal deadline, and since then, so that's cycle 2, so in cycles 2 to 4, we've had maybe more than half of those have been awarded in time. Some of them you heard about yesterday, and I think more to come in cycle 5 and beyond, I hope. But I think this is a really neat example of that sort of community effort of bringing everyone together and sharing that information and working on proposals in such a collaborative way that we've been able to get such a wealth of information. So I'm talking about stuff today that some of it's been led by me, some of it's been led by others, but it's a real team effort. It's really a lot of people. And so that was a really fun workshop. I hope we can do a follow-up of this. And so if you're interested in this kind of work, please come and talk to me so you can be on my radar if we decide to do something like this again, because I think that was really great. So off of the back of that workshop, one of the things that kind of came from that was putting together this survey and that Alex spoke about yesterday, what we're calling the DynAtmo survey, so dynamical mass part of it and the atmospheric part of it. And so this is 10 benchmark brown dwarf systems, and what you're seeing on the right is the sort of effective temperature and age cooling tracks and how these different systems sit on those cooling tracks. And actually, the target selection really worked in our favor because we kind of did cuts based on which systems were maybe not observable, which ones had already been observed. And then we kind of ended up with this beautiful sample of 10 that we spanned in sort of spectral types and masses and ages and temperatures. And so we're really going to probe and use these as substellar anchors on those cooling tracks that I just showed to kind of establish the sort of gold standard library in that wavelength range. So this is from 3 to 5 microns using NeurSpec IFU, using the technique I just showed before. And we want to kind of make this available to the community. So I'm going to show some preliminary results from this. The analysis is still in progress, so just sort of bear with us, but we're hoping to get some of this out soon. But Alex showed this yesterday in his talk, and I want to emphasize this as well because this incorporates that orbital information. So we have 9 out of 10 so far that have been observed with the program, and the red crosses, if you can even see them, especially at the back, on each of these maps here that you're seeing with each of the detections correspond to the orbital prediction of where those objects were going to be. We're not fitting for those, that was the prediction, and that's where they are. And this is how powerful it is in terms of incorporating the combination. So I think this is going to provide some really powerful results. And I'll also just show, again, and thanks to Alex for this, the 5 sigma contrast curves that we're getting from this program. Again, these are preliminary, so just take it with a pinch of salt at the moment. But we're really probing down into these contrasts. And I will say this is not chronographic imaging. This is with NeurSpec IFU. I don't want to stand here and say we don't need chronographs because that would not be in the spirit of Leo, but, but we are doing pretty well without chronographs. But we do need chronographs. We need both. We honestly do. But I'm very, even I've been really impressed by this that we've been able to get down to this. So incredible work from Alex, who's been leading the data reduction of this work. I'm not going to go through all of the spectra right now. I just wanted to flash up how beautiful this information is, and stay tuned for this work coming your way. But we're going to have, this is just a snippet from 2.93 to 3.4 micron. We have way more than this, but this is going to be a really great data set, so stay tuned for that. So the first paper that's going to come out of this is from Keelan Hoke. And again, we're coming back to the orbit fitting that we're seeing on the left here. And then on the right, we're seeing that direct detection with the NeurSpec IFU of this object. And I remember showing this to Dimitri when he was visiting STScI recently, and telling him that this was in less than 200 milliarc seconds separation without a chronograph, and he didn't believe me. So maybe that's why he invited me to come here today. But this is amazing. This is less than 200 milliarc seconds separation, and we're able to get a detection. This object is about 38 Jupiter mass dynamical mass that we get from the orbit fitting, and just to be able to do this with NeurSpec IFU is really powerful. So when you're thinking about setting up for JWST proposals, for example, or if you're maybe sitting on the TAC for JWST, think about this and think what we can really, really do with this. So in terms of the spectra from this, and again, I'll highlight that this is preliminary, but we have ground-based sphere data and gravity data as well from a program I led a year or two ago on gravity data like RF500, and in NeurSpec, and the longer wavelength range here, and this is RF 3000 wavelength range, and you can just see the wealth of data that we've got going on here, and it's just really incredible NeurSpec IFU data, and I'm really excited for Keelan's paper to come out on this, so you can all see what we're doing. But to get this level of detail at something like 180 milliarc-second separation next to a bright solar-type star without a coronagraph, I think is really powerful. So, yeah. Okay. So I want to highlight some other work as well. Kyle Franson's giving a talk in this session who's going to talk on some of this work, the so-called dynamical beacons that we call these dynamical mass objects. And I'll also highlight AFLEP that was published back in 2023 by multiple teams. And that AFLEP is like a 3.5 Jupiter mass object. So I've spoken a little bit here about benchmark brown dwarfs in that sort of brown dwarf regime, but we're not just doing this for brown dwarfs. We're starting to do some of this work for those lower mass planets as well. So Kyle and William actually had a JWST DDT proposal that was awarded a cycle or two ago. They were the first grad students, I think, to have a DDT JWST proposal awarded, which is amazing. But yeah, AFLEP, about 3.5 Jupiter masses, dynamical mass. So really being able to get down in those masses now. And then more recently, just last year, the detection of 14 Her-C, which is another low mass companion, and also go and check out William's poster as well. But the 14 Her-C is a multi-planet system and has really interesting dynamics at play. So there is an inner planet of around 9 or 10 Jupiter masses, and then this outer planet C of around 7 Jupiter masses, and we've seen an orbit fit here from Daniela and Williams' paper in 2025. And this led to, first of all, the prediction of where C might reside with respect to its stellar host, but then actually going on to being able to observe this with NIRCam chronography at 4.4 microns, so you can see the detection on the right there, as well as a beautiful background galaxy that we also get a lot of. But this is just, again, showing that using this precursor information can be really powerful. So I think there is value in trying to incorporate that astrometric information, especially the astrometry, especially from Gaia. It's already there. You're not having to write another proposal. Go and look at the Gaia information before you go ahead and sort of blindly look at these things. So 14 Her-C as being a credible detection. I'll also highlight some of the work from Thane Curry, who's giving a talk also in this session, who's been leading a lot of work using STScI Caris, and showing a couple of recent results here from HIP 99770. Is sort of a giant planet that is accelerating. You see this movie here. And also on the right, a more recent result of HIP 54515. I know Thane has a few students here that have posters, so please, again, go and check those out, go and talk to them. But I think, again, this is just talking about the realm of different detections that we have going on here and how much information we're learning, and how, increasing that detection efficiency that we're able to really start learning about these systems. And then I'll also mention as well, John Debus, we're not only looking at solar-type stars here, we're also looking for planets, or trying to look for planets around other types of stars as well, including cold planets around white dwarfs, for example. So John has been leading a program with JWST, the MEAD survey, and has a few candidates that he's been following up with Keck. And it has a poster on this, potential companions, so I encourage you to go and chat with John about this. But I've been working with John on some of using radial velocities of white dwarfs, which is a very tricky thing to do, but not impossible. And I think there's also going to be some interesting white dwarfs to potentially look at in the Gaia data as well. So highly encourage you to go and look at that. I want to present cautionary tale, though, and maybe cautionary tale is strong wording, but Elizabeth presented this yesterday, and I was speaking to Elizabeth about this at dinner, and because I mentioned the 14 Her result, and I was like, okay, you get this slam dunk prediction from the orbit, and then went ahead and imaged it with NIRCam, and it was in its predicted position, more or less, which is great. We don't always get that. Elizabeth presented this really intriguing case yesterday where the orbit fit didn't correspond to, or the orbital prediction didn't correspond to where EPS Indy was expected to be. I think the orbit prediction was sort of somewhere down here, and it's kind of like on the opposite end over here, right? And this is the caution of when you are fitting for these radial velocities and this astrometry, don't overfit what you're doing. Like, don't give it too much information. So there is a level. You can use this information, you can use this precursor information, but don't overfit. So, you know, it is powerful, but there are cases where if you're not fully confident, you might want to take imaging before you dive in with spectroscopy to make sure that the thing that you're looking at is in the place you anticipate it to be. There are cases, which I've shown before here already, where you can probably dive in with spectroscopy immediately if you're pretty confident of the astrometry and you've got good radial velocities in hand. But if that's not the case, you might be safer starting with imaging first before you go into more expensive spectroscopy, and then just ensuring that the thing that you're looking at does correspond to what you thought it was going to be. So I wanted to highlight that as well, because I think it's an important thing to think about. The other thing to think about as well, so talking about using these things as like test beds and test objects, is these benchmark brown dwarfs can really be used to test these evolutionary models and these cooling tracks. So I'm showing here a plot from Brandt et al. 2021, but I think it's a really good representation of a lot of these known benchmark brown dwarf objects in the field. And so we have a number of these objects that are consistent with our cooling tracks and our models and corresponding to the age that we would expect them to be at their given mass. But we also have a number of objects that are perhaps overluminous or underluminous. And there's still some investigation going into some of this. I think some of these objects could be explained, and I'll show a couple of slides to go into a bit more detail of that. But I think there's a sense of perhaps younger and lower mass brown dwarfs may be overluminous compared to models, while older or higher mass brown dwarfs are underluminous, potentially. And so we might be seeing a little bit of a trend there, and I think some of the work that I've mentioned with the NERSPEC program, and you'll probably recognize that a lot of these objects here are in that NERSPEC program, that will be able to use them as test objects to kind of probe this parameter space and actually sort of start testing some of these trends. So I think just something else to be aware of, but I think it also emphasizes why it's so important to have as much information about these systems as possible. I keep honing on about the mass, but actually also the age. You can get you know, a parameter constraint on the age from the host star, sometimes better than others, which you can see here in this plot, depending on how you're establishing the age. But you do get some constraints, so just something to consider. So that, for example, one of the ones in the previous plot that you may have seen is GLISA 229 system, and what we see here is on the right, we actually compared to these tracks from ATMO 2020, tracks that the single companion that was sort of like underluminous for its given dynamical mass. So measure the dynamical mass from the orbit fitting and compare that against the cooling tracks, they don't actually agree. And so there's great work from Jerry here that was published in 2024, who had gravity data. And so the interferometry data you get with gravity is incredible. I don't think I've emphasized that at all or enough in this talk, that the astrometric information, if you can do it with interferometry, then you should absolutely get astrometric information from gravity, because you really get that micro arcsecond precision. And it means that you're able to start doing these kind of test cases, and this is also with CryoRes Plus, so these are both using the VLT facility from ESO, and you can actually start to resolve that there is more than one brown dwarf here. So it wasn't the fact that this was underluminous, it was actually the fact that it's two components that are closely orbiting one another. I think, if I remember correctly off the top of my head, separation of about 16 times the separation between Earth and Moon, something like that, if I remember correctly, Jerry. And then once you actually resolve those components and put them onto the cooling track, as you see on the right there, then it actually agrees with, within the uncertainty there of where you'd expect them to be on the cooling track. And so this is another case where actually establishing the masses of these things and not just taking the model-derived mass that we often do from high contrast imaging observations is really important, because if we just took the model inferred mass, it would actually be a very different type of object that we're potentially looking at in terms of the nature of the object. Another system for which this might be the case and thanks to Elizabeth Matthews for providing the plots for this. Elizabeth and I had been working for a few years now on this object, HT4113C, and some of you may have remembered this object that was discovered back in like 2018 by Anthony Cheetham, and this is a beautiful sphere image on the right here from the detection. And over the past like decade at this point, because this was from 2016, we've taken a bunch of sphere imaging to kind of follow this object up and see is kind of similar case to what I just presented, that is the dynamical mass, you know, are we in a situation where we're under luminous like in the previous one I just spoke about, or are there like more than one component here that would take into account for that? So we think our working hypothesis is that this is an unresolved closed binary, just like 229 that I presented. The problem with this one is it's so much fainter that it's really tricky to get gravity observations. So that's the trade-off, that's the downside. But what we're seeing here is an updated orbit fit. So this is, has not yet been made publicly available, so showing this sort of for the first time, so thanks to Elizabeth. And this beautiful radial velocity curve here, and the sheer amount of data that we have over like 25 years worth of data, you'll see there's also an inner planet with a high eccentricity. That's what this sharp peaking in the radial velocity curve is here, and then this long-term drift that corresponds to the brown dwarf that we're seeing in the image here with an updated orbit fit. And the updated orbit fit does refine the parameters even further, but it actually just sort of increases the tension that we have because the dynamical mass still agrees with the previous dynamical mass that was published. We just have a tighter constraint, and models still don't agree. So we do think it's an unresolved binary, and we're also happy to chat with people if you have ideas of how we might start to resolve this, because there are gravity observations, but not to the level of detail that Jerry has in his 229 result that we would be able to do this. Okay, so sort of getting close to the end here, and I just wanted to mention a few different things. I wanted to come back to this plot because I think it's an important aspect as kind of a takeaway point. And so I'll re-emphasize what I said before, is that, you know, we're really starting to bridge these spaces between these different detection techniques, right? So those widely separated, massive, directly imaged companions that have spectroscopic information and starting to probe down in mass to more extreme contrast ratios to those inner working angles and lower masses, and Gaia DR4, which, like I said before, there's going to be an amazing Gaia DR4 talk at the next Spirit of Leo conference. I'm calling it right now, but this is going to blow us away, I think, in terms of what we're going to be able to do. I haven't really mentioned it much in this talk, but Roman, of course, that's launching later this year, is also going to be incredible. I think there's some posters here of people talking about companions that have this multi-measurement approach with the masses that would be good companions to then go and observe with Roman. So I think Roman's also going to open up a bit of a different parameter space as well, and I would love to see some of those Roman targets put onto this plot here in a future meeting so we can really start to establish this all together. And I put transits in question mark because I'm looking towards this future where the transit community and the high contrast community do eventually bridge together and become friends, and that would make me very happy. And we would be able to use this information in such an amazing way. I want the transit community to stop calling long period exoplanets anything with a period longer than 5 days, but we'll get there. We'll get there, and it will be great. So I wrote a white paper with Manazar Alam, who some of you may know, who works very much in the transiting world, of how we can start to maybe start bridging these gaps. Maybe Jada was teased the way forward. I think there's even a poster that I saw in the abstract booklet. I apologize that I didn't put your name up here, so please come find me later, who was talking about this as well. And so I think that is a future that we can work towards. So I have literally in my final minute here, so that's great. So here's the kind of takeaway points. So this multi-measurement approach provides these tight constraints to use these objects as test subjects for these atmospheric and evolutionary models as I've presented today. These precursor observations, so I'm talking about radial velocities and astrometry, increases our detection efficiency of these directly imaged companions for those targeted searches. So do consider using that information if you are planning your high contrast observations. dynamical masses, true masses, not the minimum mass, not the model inferred mass. The dynamical masses are key to fundamentally understanding the nature of the detections that we're talking about, and also things like unresolved type binaries that I mentioned. And I've talked a little bit about combining ground and space-based capabilities and a number of recent detections that I've highlighted here, and this is, as I said at the start, by no means a complete exhaustive list, but we are pushing to lower masses and colder temperatures thanks to this combination of techniques. So thank you very much.
And I was asked by Eric to ask you all, if you have questions, to give your name before. So?
Great, everything's clear.
Everything was clear. Maybe I can ask the first one.
Yeah.
You were talking about the possibility to test evolutionary models.
Yeah.
And in the example, we will get nice masses.
Okay.
But would you like to comment on the age of the system?
Yeah, so I mentioned this briefly about the ages of the system, and it depends on the star of how you do this. For a lot of our systems, we're using stellar isochrones, and so they are not always the best constraint on the age, and I think that's something we can certainly work on. Some of them do have tighter constraints on the ages, but I have people at least on the Dynamo team who are working specifically on the stellar parameters to establish better age constraints. Because yes, you can constrain the mass as much as you want, but if you don't have a good constraint also on the age, then the evolutionary model testing is difficult. Yeah.
Rachel Bounds-Rubin at Eureka Scientific. I'm curious, as we get better at, so we're doing direct imaging completely pretty much thermally right now, and we're about to go through this transition point of doing a bunch of reflected light observations. I'm curious if you, how you see this characterization changing or adding when we start to do more reflected light.
Yeah, that's a really great question. So in terms of reflected lights, we're going to start to see the aspect where we're at in the orbital phase is going to have an impact. So the optimization of making sure that we get in a point in the orbit where the reflection is as maximum as you can have it, so the chance of getting that observation is higher. But then I could also envision a way that if you observe that over a period of time, you could also pull out the orbital phase information from getting those observations. So I think that's going to be another folded in parameter that will be really powerful in reflected light observations. And again, I would love to see in the future Spirit of Leo someone talking about that, because yeah, I think that's going to be great. Great question.
Hi, Thane Curry from Subaru and UTSA. So you mentioned the discovery space we have right now. ELT is being built, and there are a lot of targets that everyone tries to look for planets that have a proper motion anomaly. We don't get a detection, and maybe they're just hiding. So and could be resolvable with a larger telescope. So could you talk a little bit about what you think in 5 years this will look like, 5-10 years this will look like with METIS?
Yes, so with METIS on the ELT, I do apologize to my ground-based folks. I was a little bit heavy on the JWST front. The ELT is going to be really powerful. I mean, the sheer size, the angular resolution that we'll achieve with the ELT versus what we're doing with JWST. Marshall showed a great comparison yesterday of the sheer size comparison. Pushing down to that resolution, the angular resolution that we just aren't able to achieve with JWST because we are constrained by the mirror size and we're constrained by the wavelength range which we're observing in. ELT is going to push down in terms of that inner working angle. There's that great plot that kind of compares the detection parameter space of ELT versus what we can do with JWST, and we're at smaller semi-major axes, smaller inner working angles, and so I think JWST is going to push sort of down in the parameter space in terms of masses and the sensitivity we can get to, but ELT is going to push sort of across the parameter space in terms of the inner working angle we'll achieve. I think we need both of those things to probe that parameter space.
Okay, question and a quick answer.
Oh, there's one over.
Okay,
Alex Venner, MPIA. There's very many things I would like to ask about, but trying to keep it focused. You were showing the example of HD4113, and you were saying that it wasn't possible to resolve the companion with gravity in the case that it might be a multiple. And I wanted to ask if there's any other modern or like near future instruments that might be able to make the sort of observations that you would like to get in that system.
Yeah, are there any near future instruments that might be able to resolve this? I'm not sure, to be honest. I feel like gravity would be the best bet, and I think there might still be a chance with gravity, and I think it would be worth honing in on the gravity thing a bit more. I'm not sure, I'm not aware of any instruments, if you have any ideas or solutions to think about this, but I think it's just so faint. It's really tricky, yeah.
Thank you.
Great talk, Emily. Kyle Franson, UC Santa Cruz. My very quick question just kind of piggybacks off of that, which is just kind of confirming that that HD4113C is too faint for cry-res or like any kind of RVs, even if you like really hammer away at it.
I think it's too faint for cry-res. We can do the calculation together. But
yeah, we should do that calculation.
Yeah, we should actually look at that. But I think, from memory, I think it's too faint. I'm also looking at Elizabeth now, who's smiling, and I think we've tried this before, and it's it's too faint. But yeah, that's the short answer.
Okay, so thanks again.
Thank you.